Okay, good afternoon. First of all, as usual, I check that the recording is working. So anybody from home, can you hear me? Okay. Okay, you should also see the screen. Okay, so good afternoon also to the again. And today we will start with a discussion on discriminative classifiers. But before we start with this, are there questions on the things that we saw before the break? Do you remember what we did before the break? Okay, so before the break, we analyzed how to transform scores to decisions, in particular, how to transform log likelihood ratios to decisions, and in general, class conditional to decision, taking into account prior information and cost of different kinds of errors, and we saw how to evaluate these things. Essentially, what we saw was that to make decisions, we rely on class posterior probabilities. With log likelihood ratios, this is done implicitly through the combination of class conditional likelihood and prior probabilities. But in the end, once we have these two, we compute posterior probabilities and we perform class assignment based on posterior probabilities and the cost of the different errors. So what we start seeing today is a different way to perform classifications where we build a model that, rather than giving us class conditional densities as we did with the Gaussian, and for those who have it in the course, the multinomial models, this is just for the computer science course, where we built a model that describes the distribution of the samples, essentially, of the feature vectors. Logistic regression, we see, is an example of model where we directly aim at computing class posterior probabilities. So we directly model the distribution of the class given the samples. That is what we were using then to make our decisions. Now, the name is logistic regression, so we discussed at the beginning what are possible tasks in machine learning. We said we have classification, and we said we had regression. Regression, we said, was something that was going from, that was used to estimate a mapping from continuous input to continuous outputs. In this case, this is called logistic regression, but it's actually a classification method. So the name regression here does not refer to the way we defined the regression at the beginning of the course. It's just an historical name. It's called logistic regression, but it's actually a classification model, where we said the goal is to create a model directly to obtain directly, given a sample, the posterior class probabilities for the class that make up our task. So for example, if we have, as we had in the Gaussian model, male and female classes, we'll get a model that gives an height, which was the feature, gives us directly the probability for the two classes. If it was the multinomial example with the cat gender, then here we would not have values, we would have something else. So the goal here is to build a model that, given the class, given the features vector, gives us the probability for the different classes. Logistic regression here works with features that are continuous, but the discriminative model idea is to build a model that directly gives us class posterior probabilities. Then we will see what are the limitations of this. Which means that we need to understand how we can model these class posterior probabilities. Imagine we have a two-class problem. So for example, the male and female class problem. from the height. So we want to know what is the probability that somebody is male given that the height is 174 centimeters and the probability that is female given the same feature vector. Now, these will be functions of the input vectors. So we will define these as functions that, given the feature vector, will output the corresponding probability. We need to understand which are good functions that we can plug here. These will be typically parametric functions, so they will depend on some parameter. We need to find good ways to describe these quantities. Up to now, what we did, we developed these quantities in an implicit way. How? We were building class conditional densities. So we were creating parametric models where the model was describing the class conditional densities. Here I put parameter theta. You have to imagine that if this is a Gaussian model, the first will be a Gaussian distribution with parameters of the male class. The second will be, again, a Gaussian distribution with the parameters for the female class. We just call these two functions. I don't need to call these two functions. So these were the two functions. So the parameters theta is the full set of parameters of the model. And of course, the first function depends only on the first two parameters, these are m, and the second function depends only on the second two parameters. But what we were doing is we were building parametric models that describe the density. Given the parametric model that describe the density, we have a way to compute class posterior probabilities, which is what, for the female, it's class conditional for female. Let's write it just like this. Times prior probability for female divided the marginal, but the marginal, remember, that is just the sum of the two joints. So this is a function that, if I plug inside the number for the height, x, and of course, these are constant that when I solve my problem are known, so these are considered to be constants that are known. Here I have a function that, given x and the parameters, gives me an expression for the class posterior probability. So we were building this kind of function here, the function that gives, given the parameters and x gives me the class posterior probability implicitly by building the class conditional densities, plugging in the class prior probabilities, and that was the function that, given x, would give us the class posterior probability. So we already know a way to build this kind of object. But we know a way how to build this kind of object through a generative model that describes the class conditional density. Now here, the idea here with logistic regression is to find a simple expression that controls the class posterior probabilities as a function of the data in such a way that, of course, this expression must be something that tells us, gives information on the kind of model that we are building. So we need to figure out how we can find models that describe this quantity in a way that does not require us to build the distribution density, but still describes some characteristics of our data that we are interested in. Now, to see how to do this, let's start and see if we follow the first route, the one that we already know, this kind of functions, which kind of shape they have. So to derive a good model for the class posterior probabilities, one way that we can follow is, okay, let's try to understand the generative models, which kind of functions f give us for the class posterior probability. So these functions f here, what do they look like for a generative model? And then we can take inspiration from there to decide to try to figure out what is a good model for this class posterior probabilities. And we start considering, again, for the moment we focus only on binary problems, then we will extend probably tomorrow because it will take some time to go through the binary formulation. Let's start considering a binary problem, and let's start with the simplest model that we have seen. We have seen generative models. The simplest model is a Gaussian model. Among all the Gaussian models, the simplest one, the one that is least powerful, so it gives us simpler classification rule, is the tied Gaussian model. The tied Gaussian model, we recall that it's a model where the class conditional, and now let's just use class 1 and class, how do I do it in the slide? H1, H0, or let's call it 1 and 0, it's the same. Or let's use the same notation of the slide. H1. So the class conditional distribution for H1 for the first hypothesis, so we have two classes, H1 and H0, if you want to call them female and male, or whatever else, or true and false, or 1 and 0. It's always the same problem. The tied model would describe our class conditional, how the class conditional given, and let's write it in this way so it's easy to remember that the class is H1 and H0. We would describe the class conditional densities in this way. So we would have the points of class 1 that are described by a Gaussian with some mean and some covariance matrix, and the points of class 0 that are described by a Gaussian with a different mean and the same covariance matrix. So here the covariance matrix is the same for the two classes. Why do I start from this model? Because this model we have seen as a nice characteristics in the terms of what? Of how it separates the classes. It's the simplest model we have seen in terms of separation rule. Why? Because we've seen that if we have this model, how do decisions look like in this model? Well, as usual, we can compute for a sample X that we want to classify the score that is the log-likelihood ratio. And then we will compare it with some threshold T. T depends on the prior information. Now, how does the log-likelihood ratio look like for the Gaussian tied model? It's logarithm of the Gaussian density for the first divided the second. So it's logarithm of what? Gaussian density. It's some constant, and now sigma here is the same, so it's the same sigma. So the first one is some constant that depends on the sigma matrix minus 1/2 x minus mu transpose sigma minus 1 x minus mu. And the second is the denominator becomes minus log of the same constant. Sorry, here it's exponential of this thing. Exponential of minus 1/2, this was mu1, x minus mu1, inverse of covariance, x minus mu1, which becomes logarithm of the constant. I have here, and here I have minus logarithm of the same constant, okay, of sigma. This go away, and then I have minus 1/2 this term plus 1/2 the second one. This term is what? X transpose sigma minus 1x plus x transpose sigma minus 1 mu1 minus mu1 transpose sigma mu1 times 1/2. And then below I have the same thing, but this time I change the sign and I have a, sorry, this is mu0, a mu0 instead of mu1. This works, these two simplify. What I have x transpose times sigma minus 1 mu1 minus sigma minus 1 mu0 plus these two terms, plus a function of mu1, mu0, and sigma. So overall, my log-like relation looks like what? I have x transpose some term, let's call this w, plus, let's call this b, which is compared with t. So what kind of decision rule is this? This is not something that shouldn't be new, because we saw exactly this like 1.5 months ago. So what kind of decision rule is? Where is the boundary here? The separation boundary. The boundary is when this is equal to the threshold. What kind of surface is this? What kind of surface is this? It's a plane that is orthogonal to W. We saw it when we discussed the Gaussian models. So we have, and if you don't remember this, then you should start studying this stuff, because this stuff is something that you should know for the exam. There will be questions on this at the exam. So what kind of separation rule we have? We have a linear separation rule. The position of the W depends on t, so different t's will correspond to different points, to different planes. The planes will be orthogonal to the direction defined by W. And then B and T control where we stop. Well, actually, B is part of the model. The threshold T controls where we put the separation rule. Why? Because this depends on the cost of errors and on the prior probability, which means that, for example, if it's more expensive to make errors of the kind I make a mistake for the point of the red class, then my threshold will move, sorry. If it's more expensive to make errors for points of the red class, my threshold will move inside the blue class to avoid that I make mistakes. Let's make it with an example where there is overlap. And this is what we saw last week. If we have samples like this may be the threshold 0, but if I want to have fewer errors for the red class, I will need to move my plane inside. So for example, in this case, my separation rule depends on t, but if the cost of misclassifying a red point is higher, then the optimal decision would probably be somewhere more inside the blue class, because I don't want to make mistakes where I wrongly misclassify points from the red class. Of course, this means that I will misclassify more points from the blue class. On the other hand, if misclassifying points from the blue is more expensive, my threshold will move on the other side. I will want to have fewer errors from the blue class, and of course, this means I will have more errors from the red one. This is embedded inside the threshold. W gives me the direction of the separation rule. Questions here. Okay, then we have seen that this is the log-like ratio for a test sample, X, a sample that we want to classify. But from the log-like ratio, if we combine it with the class prior probabilities, we can compute class posterior probabilities. How? Well, let's call this X just to avoid writing the whole LLR stuff every time. The log-like ratio represents what? It's the class conditional log ratio. So this is the value of what S is representing, which means that if now I add here on both sides the prior probabilities, the prior log odds, I get that this term here is equal to the logarithm of class posterior probabilities. Why? Because when I multiply the prior here, I multiply by the two prior, so I get the joint. Then I will need to divide by the marginal, both the numerator and the denominator, but the marginal is the same. So here this is equal to logarithm of the joint. Then I multiply by the marginal. This is the posterior for class 1, and this is the posterior for class 0. Now this term here was W transpose X plus B. So now I have W transpose X plus B plus some other term. Now this is a constant, does not depend on pi, so let's call it just C. So let's call C is the original B plus the prior log odds. It's still a linear function in X. So the log ratio of class, the logarithm of the ratio of class posterior probabilities is, again, a linear function, well, an affine function to be precise, so a linear plus a bias function of X. So we have a linear term and we add some constant that doesn't depend on X. So we have this expression. From this expression, we can compute what is the class posterior probability for the two classes. Why? Well, essentially now we solve this expression we solve this in terms of the class posteriors for H1 and the class posterior for H2. It's true that we have two terms, but we also know that they are related. So these two should sum up to 1. So what we can actually write is that this expression here is actually logarithm of the class posterior for class 1 divided 1 minus the class posterior for class 1 is a linear function. And now we can solve this for the class posterior for class 1, and then the class posterior for class 0 will be automatically obtained. To solve this in terms of the class posterior for class 1, what do we have? Well, we take exponential of both sides, we have a ratio. Now we bring this on the other side. So I remove it from here and I multiply it here. Now I take this term and I bring it on the other side, which means that I will have 1 plus exponential double transpose x plus c is equal to exponential double transpose x plus c. And then I take this term and put it on the other side, and I get that for the Gaussian type model, this expression, then I multiply both on top and on the bottom by exponential of minus double transpose x plus c. That's just for simplicity to avoid having it twice. What I get, here I have this simplifies and gives 1. Below I have this times this plus this times this, which is also 1. I get 1 divided 1 plus exponential of minus double transpose x plus c. So if you want, 1 divided 1 plus exponential of minus, let's call it s prime, a score of my x. I call it x prime because it also includes the class prior information. What we called s before was just the log-likelihood ratio. So this is not the log-likelihood ratio. This is the log-likelihood ratio plus the prior log odds. So what does it mean? The log-likelihood ratio is a function of mu1, mu0, and sigma. How are these reflected? They are reflected inside W and inside C. Then C is also a function of the prior log probabilities. So I have an expression that behaves like what? I have an expression that is a function of X, the model parameters theta, that in this case were mu1, mu0, and sigma, and the prior probabilities, let's put them also inside theta for the moment. So we have built a function that, given a set of parameters, these are known, and the sample that we want to classify, gives us a value for the class posterior probabilities. And this is the expression that we obtained, and what does it correspond to? It corresponds to a separation rule of the kind double transpose x plus c greater or equal or lower or equal than 0. Of course, assuming that the cost of the two errors is the same, but we have seen that for binary models we can always represent a problem as having cost of the errors that is the same and a prior that contains both the original prior information and the cost of the different kinds of errors. So for the moment, if it's not necessary to make a distinction, I will always assume that the cost of errors is the same. We will just see where it matters that it's not, so it's 1. We will just reintroduce them if and when it's necessary to make a distinction. So I have that given a model whose decision rule has this form, so I will have an hyperplane, W, proportional to W. C will be what? C will be a threshold that identifies where this plane is positioned over this line, so which is the actual plane. Whatever is on one side of the plane will be assigned to class 1, and whatever is on the other side of the plane will be assigned to class 0. So here, of course, this W here is W and C are a function of the Gaussian type model parameters, but that's how we obtain them. But from the point of view, geometrical point of view of what the model is doing, it's separating my planes with a linear classification rule. And if the classification rule is linear, this is the expression that we get for the class posterior probability. So we have that what we derived here was starting from the Gaussian model, but then we never used any information on how this W was obtained. Whatever we derived would work for any W. Probably except for W equal to, no, even for W equal to 0 should work. So we have that if our separation rule has this form, which means that the separation boundary, this is the separation boundary equation, is a linear separation rule, then the class posterior probability for class 1 given x will be 1 divided 1 plus exponential of minus W transpose x plus b. Now this function has a name, function 1 plus exponential of minus s. It's called sigmoid function. So the sigmoid function relates what? The decision rule with the class posterior probability. If I have a decision rule of this kind for a given value of W, this will correspond to a class posterior probability that is sigmoid of that term. Notice that from the geometrical point of view, we are actually making a slightly stronger modeling. Here, if we look only from a geometrical point of view, I have an infinite set of W's that correspond to the same direction. So here, the posterior probability depends also on which kind of these W's I obtain. So there are solutions that, if I just draw the separation rule, seems equivalent, but from the point of view of the model are not, because the magnitude of W influences the class posterior probability. So for us, the decision rule is the full W, including their magnitude. So see here. If I have a decision rule with these parameters, this corresponds to a classification rule where the class posterior probabilities are sigmoid of, sorry, here it's always C, of this term. And of course, geometrically, I may have different W's that correspond to the same boundary. The boundary can be the same, but the classification rule can be the same, different. So for example, if I have W prime equal W half and C prime equals C half, the separation boundary is the same, because this is obtained with the same set of x as before, because I can remove the 2, but the decision boundary is the same, but the decision rule is different because the magnitude corresponds to different class posterior probabilities. This will affect the way we modify the problem when we will see why this is important later. For the moment, remember just that there may be solutions that have the same separation boundary, but if W and C are not the same, they are not the same model because they correspond to different class posterior probabilities. We'll see why this matters later. In any case, what have we done? Essentially, we have found a way to relate a simple expression that tells us how we separate the classes with a decision boundary that corresponds to that equation and a decision rule of the kind I compare this with 0 with class posterior probabilities. So we have now a model that if I give you a value of, x and c, if I give you a value of W and a value of C, this gives me a class posterior probability. So we have now a model where our class posterior probability is a function of x and the model parameters which can be interpreted as being W and C. When we did the derivation with the Gaussian model, these W and C were actually themselves functions of the class means and covariance matrix. So with the Gaussian tide, we had the W was a function of the model parameters, and C as well. But if I forget about how I get W and C for the moment, and I just tell you I have W and C that represent my separation rule, that is all I need to define class posterior probabilities. And once I have class posterior probabilities, I know how to make optimal decisions. Notice that optimal decisions are obtained by comparing this with 0. However, if we want, we can. If we don't want to use effective prior, and here C contains the real prior of the application, we just need to modify this to take into account the cost of the different kinds of errors. So we just need to change the threshold. So in any case, once we have a model for class posterior probabilities, we can, if we want, reintroduce different kinds of costs. Everything we discussed before the holidays remains valid. Once I have class posterior probabilities, I don't care where I got them from. I can use them to make optimal decisions based on class posterior probabilities. We've seen that for generative model, we can separate the contribution of the cost of errors of the likelihood ratio and of the prior probabilities. Here we do not have that separation anymore because we have just the class posterior probabilities which embed inside a class prior, and then we will discuss which class prior later. But in any case, once I have the class posterior probabilities, I can take into account the cost of errors if I want that may not be 1, and take optimal decisions as we saw at the beginning of the lectures on bias decisions. Now, where is the gain? The gain is that before to build this model, we had to go through a generative model that gives us implicitly W and C given the characteristics, the model for the distribution of the feature vectors in the classes. The idea behind what we will see now is to ignore the distribution of the feature classes and try to directly obtain the values of W and C that provide a good classification rule. So we look at it from another point of view. Rather than building a model for the features that then corresponds to a set of W and C, we forget about the distribution of the features and we try to find a good set of W and C that provide a good separation for our classes. So rather than describing how these classes are done, what we look for is simply if we can find a good separation, a good plane that separates our classes. Notice that with generative models, we have a description of the features. So once we are able to build a good generative model, we have much more information on how the distribution of the features. But with a descriptive model, we can overcome the problem that building good models for the feature distribution is actually harder. To make decisions, what we really care is to be able to compute class posterior probabilities. So we can, for example, decide that regardless of the distribution of the feature, we want to use a linear separation rule. So in our case, the assumption of the model assumption is that the decision rule will be linear. So we will assume that this is the decision rule, and we will also assume that this decision rule corresponds to the logarithm of the class posterior probability. So we will assume that this is true for some W and some B. So rather than assuming a distribution on the features, we assume that the decision rule is linear. The decision rule, we use a probabilistic interpretation. So we give a probabilistic interpretation to the decision rule. The W transpose X plus C term here represents the logarithm of the class posterior probabilities, which implies that the class posterior probability for class 1 is sigmoid of W transpose X plus C. And from a separation point of view, it corresponds to selecting separation rule between the classes that are linear. And of course, if I want to account for cost of errors that are not equal and are not equal to 1, then the actual decision may move inside the space of one class, because as before, if I expect to pay more, if I make more errors for one class, I want to reduce the amount of errors that I make for that class, even if that means that I will have more errors from the other class. However, notice that we choose the decision rule, but we don't need to make any assumption on the distribution of the features. For example, if we have data distributed in this way, using a Gaussian model is probably not going to do a very good description of our data. A Gaussian model fitted here would give me something that has a mean here, and the covariance matrix that probably looks something like this, and something like this for the second point. So there are regions in space where I don't have samples, but the density will be high. There are regions in space where the density will be low compared to the number of samples that I have, so my decisions will not generally necessarily be very good. Now, depending on the data that I have, a Gaussian model may still do well enough, but in this case, probably if I just decide that a linear separation rule is enough for my data, I can try to figure out if I can do better than what I would have with a poor tight Gaussian model. Here, a tight Gaussian model would actually look something like this for both classes. In any case, I can probably do better than what a Gaussian model can do if the distribution of the data is not well modeled by a Gaussian. So the assumption is linear decisions. This is the decision rule when the cost of errors are assumed to be 0. This is the separation boundary when the cost of errors are assumed to be, the cost of errors are assumed to be equal or 1. But even equal is enough, because what matters is the ratio between the two cost of errors. And this represents, so these are the assumptions. Well, actually, this assumption derived from the fact that this represents, and this is the main assumption, that this term represents the ratio between the class posterior probabilities. All these things are a consequence of this. So this is the assumption. I have a linear decision rule that represents the class posterior probability ratio, the logarithm of the class posterior probability ratio. Consequence, this is the decision rule, and this is the boundary. Now, the problem here is, okay, all this works once I know W and C. The question is, how do I obtain W and C without resorting to a description of the feature samples? So how I can get a separation boundary that is good without actually modeling how the data are distributed in space. Okay, before we see that, one thing that I forgot to say, sigmoid function looks like this way. Remember that the sigmoid function links what? The class posterior probability for class 1 to this term. We'll also call this term the score for the logistic regression model. So this will be the score of the logistic regression model. So it links the score S to the class posterior probability for class 1. And of course, the class posterior probability for class 0 is 1 minus sigmoid. Now, the sigmoid function has this S-like shape. It takes value 1/2 in 0, which makes sense, because remember that when this is 0, it means that I'm on the classification boundary. Assuming that the cost of errors is the same, the classification boundary is obtained when S of x is equal exactly to 0. But if I'm on the classification boundary and the cost of errors is the same, that means that the class posterior probabilities are the same. If I'm on the decision boundary, it means that I cannot choose between the two classes, which means that the posterior probability for the two classes is the same, which is exactly 1/2. So when the input of the sigmoid is 0, the output is 1/2, and indeed, this is consistent with the fact that I'm exactly at the decision boundary. The class posterior probability for the two classes is 0. Then, the class posterior probability for class 0 is 1 minus the sigmoid, which corresponds to the sigmoid of minus the score. This also makes sense. We did the model assuming that W points towards class 1, so the posterior probability of class 0 is 1 minus the sigmoid. However, if I did the same model with W pointing the opposite way, I would have that H0 would be the class on top of my ratio, and I would have exactly minus S as a result. So this tells us that the model is treating in a symmetrical way the two classes. So it's expected that it behaves in this way. And finally, okay, this we will probably not need, so we can skip it. Then we have that as we move towards larger and larger scores, the sigmoid becomes larger and larger, which means that indeed the class posterior probability, as the score increases, this goes towards 1. Asymptotically, this will tend to 1, and on the other side will tend to 0. This is correct. Remember what is the score. The score equal to 0 means that I'm exactly on the boundary. The score is positive means that I'm inside the boundary on the side of class 1. So the posterior probability for class 1 is larger. The farther I am from the decision rule, the larger the score. The farther I am from the decision boundary, the higher the posterior probability that the sample is from class 1. This makes sense intuitively. If I'm far from the decision boundary, I'm more sure that this point belongs to class 1, to the class red. When the score is negative, I am in the region of class 0. So the posterior probability of class 1 will be lower than 1/2, and the more I move towards a negative score, the more the posterior probability for class 0 increases, which means that the posterior probability for class 1 goes towards 0. So the sigmoid reflects exactly this trend. Now, as I said, the problem that we have to solve is how we will estimate the model parameters W and C. Before it was C on the whiteboard, here it's B, but okay, on the whiteboard it was the opposite. I was using C for the original log-like ratios and B for the constant, but it's just the name of the constant. So from now on, what I was calling W transpose X plus C, we call it W transpose X plus B. The value of B and C doesn't matter. We're going to estimate them in any case. So whatever it represented originally doesn't matter anymore. So we have a model that is described in this way. So rather than call it C, the bias, we call it B. This has nothing to do with the original B that I was using at the beginning of the lecture. This is just the model that we will use. So rather than having sigmoid of W scores S plus C, we will call it in this way. So we need a way to figure out the values for W and B. We know that these represent linear surfaces, but we need to find how to estimate values of W and B that are good for our task. Since we are using we are trying to do this in the framework of machine learning. What we will try to do is to devise a way to learn the good values of W from the data. So we'll try to estimate what are good separation rules directly from the data. So as we did for the generative model, we will try to estimate the values of W and B directly from the data, but in this case, the model will be obtained to estimate a good separation rule without requiring us to make assumptions on the actual distributions of the feature samples. Again, we follow a frequentist approach, which means that we will look for a set of W and B for an estimate of, we will assume that there are optimal W and B, and what we get is an estimate for these W's and B obtained from a training set. So, as we did up to now, we assume we have a labeled data set, and again, needs to be labeled because we need the labels to know which samples are from class 1 and class 0, and then we make the usual assumptions. The samples are ID. They follow the same distribution, which is not what is written here. Here is written that they are independent, but the samples are independent given the model parameters. So once I know the model parameters, knowing one sample will not give me any information on the other. And they have the same distribution. So once I know the parameters, well, this does not require that I know the parameters, but all these are distributed in the same way. These are the same assumptions that we made for the generative model. There is nothing new. But this time, the model parameters are directly W and B. Now, to find values of W and B, we can, again, look at the likelihood function. The likelihood function, we will see that a way to estimate W and B will be to maximize, in order to estimate those W and B that maximize our likelihood. Remember that the likelihood function has this expression. This is the same likelihood function that we were writing for generative models. I will try to make generative, for example, Gaussian model. Likelihood function is, let me just see if I did it, yes, is the joint density for all the class observed samples and corresponding class labels given the model parameters. In the Gaussian model, theta was, let's keep it with the tide, were these three parameters. The likelihood now is still the same. The likelihood is a function of the model parameters, and is the value of the joint density for all the samples and the observed likelihood given the model parameters. In this case, the model parameters are W and B. Now, how can we express the maximization of this function explicitly in a way that shows us the contribution of W and B? Again, I will go with the parallel. In the generative model, so what we did before the break, well, in both cases, we work with the logarithm of the likelihood. Well, let's do it in 2 steps. First step, in both cases, is the same. We use the ID assumption, which tells us that the joint density, given the model parameters, factorizes as a product over the single samples. The product over samples of the density of the corresponding sample given, sample including feature vector and label, given the model parameters. In the discriminative world, it's the same. I have the factorization that is exactly the same. My likelihood factorizes over the samples. This, we did it already for the generative model. For the logistic regression, up to now, I didn't use any other assumption than the IID assumption, so it's the same. And since they are identically distributed, all these densities here are actually the same density. So I can drop here the indices. Of course, each time they are computed at the value of another sample, but the density function is the same for all the samples. And this remains the same for both models. So now what matters is how I model this. What changes between the two models is how I model the joint density. In the generative mode, the joint density was factorized how? As a class conditional. Let's write it as usual, like this. Which depended on the model parameters times a prior probability. The model parameter was influencing only this term. This time, we use the opposite factorization. We have a joint. Remember that when I have a joint density, let's do it with probability. If I have a joint probability, I can write it in this way, but I can also use the other factorization. I can write it in this way. Both are the same. This is what we did for the generative. If this is the sample and B is the class, this is the factorization that we use for the generative. For the discriminative, we will use the other. So this function will be probability of the class given X, and let me put some spacing here, times the marginal for X. Now, which of these depends on the model parameters? Well, just the first term. The marginal here does not. The marginal for the samples does not depend on the model parameters. The model parameters tell us how to compute this term. So they fully specify the first term. The second term is not specified. In the generative model, the second term, what we didn't specify was the class prior probabilities. And we saw that it was not necessary to specify them at training time because they do not depend on the model parameters. In this case, what we don't specify is the density of our feature vectors. Which means, and then I will stop for a break, that our likelihood becomes what? Well, let's go in the log. So let's take the logarithm of both. So we work with the logarithm of the likelihood rather than with the likelihood. For the generative model, we have a sum of what? Logarithm of this term. So we have logarithm of class conditional density plus sum of logarithm of prior probabilities. And on the other side, for the discriminative, the log likelihood is the sum of the logarithm of the class posterior probabilities plus the sum of the logarithm of the class of the sample marginal. In both cases, our solution was to find the maximum of the likelihood with respect to the model parameters. In the generative world, this means that we maximize the first expression because this does not depend on the model parameters. In the second, in the discriminative world, this is what we need to maximize because we can see this does not depend on the model parameters. So what happens is that once we have a model for class posterior probability, we can find optimal W and B according to that model without ever needing to specify what is the density distribution of the samples. So we can find W and B. To do that, we don't need to specify what is the distribution of our samples. Our maximum likely solution does not depend on the distribution of the samples once we have defined the model for class posterior probabilities. Now let's make a break here and then we will see how to go on with the estimate of this. Okay, let's start again. For those who wrote on the chat, yes, the microphone was muted because I was not going on with the lecture. I was answering to a questions, but I forgot to stop the recording. So what you saw in the last probably 10 minutes were just answers to people who were coming to the desk. I didn't go on with, I was not explaining anything new to the class. Okay, so, no. Okay, so let's resume. Let's check everything is good for the recording. Yes. Okay, so before the break, we arrived to the point where we said that our goal is the maximization of the log likelihood. And now we'll go quickly through the slides because the slides just summarize the same thing that I wrote before. We started from the data likelihood. We use IID independence to factorize over samples. Then we use our factorization, the opposite of the generative model. So this time we factorize the joint feature and class distribution as a class posterior probability times a feature marginal. The feature marginal in this case does not depend on the parameters because the parameters directly describe the class posterior probability, which is the only object that we care for classification. Then the log likelihood becomes a sum of the log posterior probabilities computed for the samples in our dataset plus a log marginal that we can ignore because our goal, if our goal is to maximize the log likelihood, the log marginal does not depend on the model parameters, so we don't really care about its value. Which means that the function that we maximize is the sum of the logarithm of the class posterior probabilities. If you want, we are maximizing the conditional probability of the logarithm of the conditional probability of the classes, of the observed classes given the corresponding sample. So for each sample here, we will have a set of samples, x1, c1, x2, c2, x3, c3. For each sample, we will replace, for example, for the height model, this will be the samples. Our log likelihood, the function we want to maximize, will be logarithm of the probability of m given 174 plus log probability of f given 174 plus log probability of m given 180. Now the problem is, well, these depend on the model parameters. So to maximize this with respect to the model parameters, we need to make explicit the dependency of these terms on the model parameters. The model parameters give us what? Tell us that if the class is H1, and now we will use 1 rather than H1, because for the moment the numerical value for the label was irrelevant. Now we will use the numerical value for the label explicitly. So for what comes afterwards, we will label class true or class H1 as class 1, and the other we will label it as class 0, and we will use numerical value. So we assume that CI is either 1 or 0. Our model gives us what? Gives us the probability that a sample, that the class is 1 given a sample. This is described by our model. if I plug here an xi value and a set of model parameters, this is the value that the model computes for the posterior probability of class 1. And from class 0, we have seen that it's the opposite. So if we have W and B, we can take our data set and we can associate to every sample a value Y, which is what? That's the probability of class 1 given Xi. So Yi will be a value that for each sample Xi gives us the probability that the sample is from class 1 given that corresponding feature vector and the model parameters. Notice that we could use sigmoid, but in many books you will find it called Yi, and we use Yi because our expressions will become long, so we don't want to avoid to bring every time this term. Remember that Yi depends on W and X. 1 minus Yi is the probability that the class is 0 given the feature vector Xi and the model parameter W and B. So Yi is a function of Xi, W, and B. Actually, we write just Yi, but remember it's a function of these three terms. Here there is a missing I in the formula. What is the distribution of the class given Xi? Well, we have a model that says that the probability that class I is 1 given Xi, W, and B is Yi, which is sigmoid of, but this time we write it explicitly like this, and tell us that the probability of class being 0 is 1 minus Yi. Which kind of distribution is this? It's a Bernoulli distribution with parameter Yi. So our model is actually representing the class posterior probability as a Bernoulli distributed random variable where the parameter of the distribution is a function of the feature vector and the separation rule, the parameters of the described separation rule. So we have that a class posterior probability is modeled by a Bernoulli random variable with parameter Yi. Yi is what? It's sigmoid of W transpose Xi plus B. Now we can use this to do what? To compute our log likelihood. Our log likelihood looks like what? Well, the log likelihood the log likelihood, well, here we start with the likelihood, but okay. The log likelihood is the logarithm of let's write it in this way. It's the logarithm of the product of the class posterior probabilities for the observed samples. If you want, we can put the product outside. We have a sum over samples. If we put the sum inside the logarithm, it becomes a product. So if we have, for example, our male 174, female 174, and male 180, our log likelihood will be the likelihood of what? Or if you prefer, we can even do it with the sum. This will be with the sum. With the sum of logarithm of probability that C1 is equal to male given X1 is equal to 174. So let's remove the sum because I will write it explicitly. Plus the logarithm C2 is female when X2 is 174. Plus log probability that C3 is male given that X3 is 180. This is the log likelihood function for the class labels using the model that describes the class probability given the feature vectors. Each of these is the probability of a Bernoulli distributed random variable. Now let's call M and F 1 and 0. Which one you prefer to be 1, male or female? Choose one. What? Okay, so female 1, male 0, which means it is 0, 1, and 0. So that's the likelihood that we want to compute. This is the probability distribution of a Bernoulli. So technically, this we could write as logarithm of 1 minus y1 plus logarithm of y2 plus logarithm of 1 minus y3. Or if you prefer, logarithm of 1 minus sigmoid of W transpose x1 plus b plus logarithm of sigmoid of W transpose x2 plus b plus logarithm of 1 minus sigmoid W transpose x3 plus b. Now, here you see that it's not, what's not nice is that I have this logarithm, this asymmetry in the way we treat terms. Now, this is not strictly necessary, but for conveniency reasons, rather than using explicitly the function, remember for a Bernoulli random variable, if C is a Bernoulli with parameter P, we have that this is P, and then we have that the probability that C equals 0 is 1 minus P. We have seen that we can write this in a compact form as what? Well, if A is the value for which we compute the probability, we've seen when we discussed the Bernoulli distribution that we can write the probability that C is equal to A in this compact form. If A is 1, only P remains. If A is 0, then only 1 minus P remains, with the convention that 0 to the power 0 corresponds to 1. So it's a limit, and then we take the limit value of the limit, which is 1. Now, if we adopt this convention, we can write each of these terms how? Well, this is C1, this is C2, and this is C3. So the first term becomes what? The first term is the probability of a Bernoulli with parameter y1. So I will have y1 to the power C1 times 1 minus y1 to the power 1 minus c1. It works, and then I have the logarithm of that. C1 is 0, so what remains is exactly 1 minus y1, what I was writing here. Then I have, for the second term, y2 to the power c2 times 1 minus y2 to the power 1 minus c2. C2 in this case is 1, it's correct, what remains is y2. And then for the third one, it's the same. I write it here. You cannot read it well, but it doesn't really matter. It's the same. So in general, if I have my data set, each term, or to be precise, how we wrote it on the whiteboard, this would be sum of the logarithm of yi ci times 1 minus yi to the power 1 minus ci. Yi is a function of the sample and of the feature vector and the model parameters. Ci is the numerical value that we associated to the class. This is why we needed this to be numerical now, because we need this to be either 1 or 0. Otherwise, mathematically, this would not make sense. Taking the log, I have the logarithm of a product. I split it into logarithm. And then this, I take the exponent outside, and what you have is what is on the slide. The log likelihood can be expressed in this form. This yi is a function of the feature vector and w, and this is the same, of course. So this is the function that describes the likelihood. This is how you would typically find the model described, our goal is to maximize this expression with respect to W and B. So we have this expression that depends on W and B through Y. So given a value of W and B, then we can compute all the yi's for all the samples, and given all the yi's and the values of C, we can compute the value of this function. So our goal is now to find the maximizer, the function that, the value of W and B that maximize this function. This is the maximum likely solution to the problem of estimating the separation rule. What does it represent? It represents the separation rule under which our class labels are more likely. So we have a model that tells us how we assign class labels, what is the probability of the class labels for the different samples that we have in our dataset. We find W and B under which the class labels that we have observed have the highest probability. This is similar to what we did before we started seeing classification models when we were talking about maximum likely solutions. The first example that we made was tossing a coin. We were looking for the parameters P of the probability of the coin given head that maximized the likelihood of the tosses that we observed. If we had observed head, tail, head, head, and tail, we would find a P under which this set of observation was maximum. There was probability of head equal 3/5. The idea here is the same. We'll find the parameters of the Bernoulli distribution that maximize the probability of the label that we have observed. The only difference is that we don't have a single parameter P for each class, but the parameter that describes the class label Ci is itself a function of the feature vector. So the only difference is that when we started discussing, we had that a toss was described by a Bernoulli with parameter P that was the same. Here, each class condition is described by a parameter by a Bernoulli, but the parameter of the Bernoulli is not the same for all. The class label depends on the feature vector. Different features will have a different probability of being from one of the two classes. But the idea behind is the same. Once I have my observed labels and the corresponding feature vectors, I can try to find the parameters W and B, because remember that all these yi are connected because they all share the same W and B parameters. So we look for the parameters W and B that jointly maximize the probability of all the class labels that I have observed given the feature vectors that are associated to those class labels. Questions? Okay, now this is the solution that we want to compute. We will see that finding a solution to this problem is actually not that straightforward. We will see how to do it later. Now, before we see that, it's interesting to analyze another couple of interpretations of this objective. So logistic regression looks for a separation rule described as W and B. This is the set of points where W transpose X plus B is equal to 0. Whatever is on this side will be assigned to class red, and on this side to class blue, to class false, of course, assuming that the cost of the two errors is the same. Otherwise, this will influence where I need to put the threshold. So geometrically, this is what it's trying to do. We have a connection between the class and the model parameters W and B, and we have a way to estimate the model parameters that we've seen can be interpreted as a maximum likelihood solution that maximizes the data likelihood, which we have seen corresponds, according to the model, to the maximization of the probability of the observed labels given the feature vectors, which corresponds to the maximization of the data likelihood, so the likelihood of the feature vectors and the class labels, because we have seen, maximizing with respect to the model parameters, the maximum does not depend on the actual distribution of the feature vectors. Now we can link partially, because we will not do the full link, because that would be quite more complex to do, but we can relate in some way this objective function to what we have seen in bias decisions. Now I will actually give this interpretation. Maybe the link with what we saw will not be necessarily clear, neither I want to go into the details of that. I will just recall a couple of things when needed, because they would be too hard. But in any case, we can interpret our objective in another way that on its own is interesting, and then we will see how much we want to link it with what we saw last time. Now, maximum likelihood is the solution under which the observed class labels are most probable. We can show that we can interpret this maximization as a minimization of another quantity. How? Well, maximizing this function corresponds to minimizing minus the function. If I have the maximizer of f is equal to the minimizer of minus f. Imagine that you have your function f. This is not a good example, because the maximizer of f is the minimizer of minus f. This is f, and this is minus f. This is theta here. So minus f is the reverse of the function, and the minimizer of minus f is the maximizer of f. So I can actually solve my problem by looking for the minimizer of minus this expression. Why would I want to minimize this expression? Because this is a sum over sample of a quantity that has a particular interpretation. The quantity that is inside the summation, so for one sample, can be interpreted as a binary cross entropy between what is called the distribution of the observed and predicted labels. What do we mean? We mean that yi represents what? This is the probability of class 1 given xi. So we can interpret yi as the probability of the class being 1 given xi according to our recognition model R. Ci is the actual label. So Ci represents in some way, we see how, the distribution of the actual labels of my dataset. Now, to see how these are involved and how this gives way to a cross entropy, because you may imagine that Ci is actually a number, so why am I talking about two distributions? We will see it in a moment. First of all, let's see what is the cross entropy itself and what it encodes. Let's imagine we have two distributions, P and Q, defined over the same domain, but for us this is not a problem because we have Bernoulli random variables, so domain is 0 or 1. Cross entropy is minus the expectation over P of the logarithm of Q. If it's discrete, the expectation becomes a sum over the support of the two distributions of minus log Q of x times P of x. So it's the expected value of minus logarithm of Q. Which are the distribution P and Q in our case? Well, Q is easy. Q is the distribution of the class label given the sample and the model parameters. So it's the distribution of the class label given according to our classification model R. What is the distribution P, the one we take in the expectation over? It can be interpreted as the empirical distribution of the class label. That is a distribution that has value 1. The probability of what I observed is exactly 1, while the probability of what I didn't observe is exactly 0. Again, we can interpret this as the probability that somebody who knows the complete model, so who knows the labels, in this case, who knows the real word, would put for the sample yi. The sample yi is a class that is what? The probability that the class 1 is exactly 1 if 1 is the class of the sample, while if the class of the sample is 0, what is the probability that the class label for the sample is 1? Becomes 0, because I know that the label is actually 0. The same, if the label for the sample is 1, what is the probability that the label of the sample is 0? Then it's 0, because I know that the label is 1. And the same, if I know that the class label is 0, what is the probability that the class label is 0? It's exactly 1. Which, if we encode all these expressions, we can see that the probability that the class is 1 given xi and perfect knowledge of the data distribution is exactly Ci. While the probability the class is 0 is 1 minus small ci, where ci is the class. So we can interpret this as a cross entropy between what? Between the probability of an evaluator who knows the real label and the distribution predicted by our recognizer. So the logistic regression is trying to minimize the cross entropy, the average, because then we are taking a sum over samples. And why do I use average rather than sum? Because minimizing this function is equivalent to minimizing the function where I put 1 over n in front. 1 over n is a constant, so if I divide the value of the function by n, it will not change the minimizer. So I can consider minimization of this expression as minimization of the average cross entropy between the distribution given by our model and the actual empirical distribution of the data, of the training set. Now, this cross entropy measures a goodness of the prediction. We can also give another interpretation where this average is actually, okay, well, I will not go into this. Okay. In any case, the cross entropy is minimized, we can show, when the two distributions are the same. What does it tell us? It tells us, this important thing, that the cross entropy measures a difference. It's not a distance because it's not mathematical distance, but can be interpreted as a way to measure how much two distributions are different. It's not symmetric, but in any case, if the cross entropy is large, then the two distributions are different. If the cross entropy is 0, then the two distributions when it's minimized, the two distributions are the same. It's not 0, it's minimized. And since our goal is exactly to minimize the cross entropy, we are imagining that we are trying to get our model to give a prediction that is as close as possible to the empirical one. So, with the constraint given by the model will try to tell that all samples from class 1 have a high posterior probability, because ideally the difference between the empirical and the model posterior probability would be, the cross entropy would be among all possible solutions. If my model is completely free, will be minimal when the model gives exactly the evaluator posterior distribution, so the real distribution of the data. So the model will try for the empirical to match the empirical distribution of the data. So the model will try as much as possible to say that the points from class 1 have a high probability of being from class 1. Points from class 0 will have a high probability of being from class 0. Because ideally, if the model was free, it would obtain the minimum of the cross entropy whenever it was able to say that all points from class 1 have a class posterior probability of 1, and all points from class 0 have a posterior probability of 1 as well, for class 0 this time. So this is what the model would like to achieve, because that would be the minimum of the cross entropy. The model is not free because the shape of the distribution is controlled by our assumptions. So the model is not free to give any value that it wants for any sample. It's trying to give large posterior probability for class 1 and low posterior probability for large posterior probability for class 1 to the sample from class 1, so from the red one, and low posterior probability for class 1 for the points of the other class, within the constraint of what the model allows it to do. The model does not allow it to have large posterior probability necessary for all the points. Why? Well, imagine, for example, we have a data set like this. Remember what the separation rule represents. The separation rule represents the point where the two class posterior probabilities are the same. If the classes are not separable like this, so that means that here, however I put a plane, I will have points on the wrong side of the solution. Wherever I put my separation plane, remember that on one side all the points are labeled as red, on the other they are labeled as blue. Whichever W I choose, I will have some points on the wrong side. But if a point is on the wrong side, it means that the model will have, for example, let's take this red point here. I will have a red point for which the probability of class 1 will be small. Let's say close to 0. So the model is trying, and the farther is this point from the separation rule, the smaller this posterior probability will become. So the model will try to do what? Will try to avoid having points that are on the wrong side of the separation rule, and especially far from the separation rule itself on the wrong side. It's trying to put a separation rule so that all the points are on the correct side. Sorry. And if it can't, as in this case, it's trying to limit the points that are on the wrong side. So these points here, as much as possible, with points being far in the wrong position of space, which are actually more misclassified. This can be seen by the cross entropy. The cross entropy wants that points from the red class have a high value for this, and points for the blue class have a low value for this. So we'll try to do that as much as possible, which means that solutions where points from the red class have a low posterior probability for class 1 will be solutions that have a large cross entropy. So a solution that the model will try to avoid because we want to minimize the cross entropy. Ideally, and we will see that this can be achieved in some case, if points are, for example, distributed in this way, ideally, I will look for a solution that separates the classes and gives posterior probability 1 for all the points of the red class, and posterior probability of class being 1 equal to 0 from the point of the blue class. And we will see later that this is a problem. So the minimization of the cross entropy says that we are trying to find a distribution of the label according to the recognizer that is as close on average as possible to the empirical distribution of our data set. Now, the empirical distribution on the data set can be itself seen as a proxy for the distribution of the class label for evaluation data as long as our training set can be interpreted as samples from the data that we want to classify, but I will not open this additional parenthesis. Now, this process can be interpreted even better. So this is minimization of the cross entropy, but we can also rewrite the cross entropy in a way that shows exactly this phenomenon, that the model will try to avoid solutions where points are misclassified. How? Well, minimization of the cross entropy can be, because we can manipulate the cross entropy to give yet another interpretation of the logistic regression objective, which shows what it's trying to do for each sample. How? Well, we rewrite the cross entropy, but now instead of using the original class label, which were 0 or 1, we use a new labeling that is +1 for points of class 1 and -1 for points of class 0. So if the point was from class 1, we keep the label 1. If point was from class 0, we use label -1. So this is the new labeling. We see why in a moment. Now, this is the objective function that we want to minimize, or if you prefer, we set average cross entropy, so we can put a 1 over n in front of this. Each term is the cross entropy between the predicted label and the empirical label distribution for the recognizer and the evaluator. So the empirical one or the recognizer one. It's a parameter of W and B and X through Y. Now, let's rewrite it, and now we use SI, that is the score of the logistic regression model. We call it S of Xi before, now let's call it SI, just to avoid putting the function of X. So SI, and we will see why in a moment, is W transpose Xi plus B. This is the original cross entropy we started from, which, if we remember what is the value of C1 and Y1, is what? When the class is C1, I will have only the first term, because this will become 0. So if the class is C1, I will have minus logarithm of Yi. Remember that Yi is sigmoid of W transpose Xi plus B. So it's sigmoid of Si. And when Ci is equal to 0, this term goes away, and I have minus, this is what? This is 1, 1 minus 0 is 1, so I have minus logarithm of 1 minus Yi. 1 minus Yi is 1 minus sigmoid of Si, which we have seen, sigmoid of Si is sigmoid of minus Si. So this is the term that we have. Now we observe that this corresponds to what? Minus log of sigma Si when the class is 1, and sigma minus Si when the class is 0. So if we call the class 1 and minus 1, we can write compactly both expressions in this way. This is what? Well, when Zi is plus 1, then I have minus logarithm of sigma of Si. And once the die is minus 1, I have minus logarithm of sigma of minus Si. So exactly the function that I had before. Now I substitute back, I don't really need it, but I substitute back my Si, or if you prefer, I have minus logarithm of sigma Zi Si, which I write as minus logarithm. Let's put the sigmoid exponential of minus Zi Si in this way. Now bring this minus inside the function. Minus logarithm corresponds to taking the inverse of what is inside the logarithm, which means logarithm of 1 plus exponential of minus Zi Si. And then if you want, you can rewrite Zi explicitly. So this is the cross entropy for one sample. Our objective function is minimizing of, let's put 1 over n. the sum of the cross entropy. So minimizing these terms here. The average log loss. This is called log loss. So it's an average of these terms, each computed for one sample. Remember that SI is also the score. The score corresponds to W transpose X plus B, corresponds to logarithm of the class posterior probabilities. All these terms are connected. So this is the meaning of the score. We call it S of X as well. Now this function is called logistic loss. Sorry, the function log of 1 plus exponential of minus, let's use letter alpha, as a function of alpha, this is called logistic loss. Let's use L because L for loss. These are loss, and our goal is to minimize the logistic loss computed on this kind of input, the average logistic loss over our dataset. Now we are taking an average of these terms. Let's look what do these terms represent, how they look like. This is the logistic loss as a function of, let's write alpha to avoid confusion with the sample. So this is the function logarithm of 1 plus exponential of minus alpha as a function of alpha. We observe that this function behaves how? When alpha is large, this function behaves like logarithm of, remember the logarithm of 1 plus x, when x is small, behaves similarly to x. So when alpha is large, exponential of minus alpha is a small number, so the function here asymptotically behaves like the exponential of minus alpha on this side. On this side, how does it behave? When alpha is large negative, here I have an exponential of a large number, this becomes similar to logarithm of exponential of minus alpha. So approximately, it's approximately minus alpha. So on this side, asymptotically, it behaves like minus alpha. And of course, here where alpha is neither large nor small, it will bend and obtain something that is between those two behaviors. So we have a function when its input is large, it will asymptotically decrease in an exponential way. When its value is negative and large, it will asymptotically increase in a linear way. Now we can interpret this as what? Well, remember that what I'm doing is an average of the logistic loss computed at Zi Si. What is Zi Si? Well, remember that Si is itself the class posterior probability. And our decision rule is when Si is greater than 0, I will predict 1. When Si is lower than 0, my model predicts class 0. Okay? So this is what my model is doing. And actually, my model is saying that the probability of class being 1 given x is sigmoid of, given xi is sigmoid of Si, which depends on xi. This is the probability of the class being 1. And my decision rule is compare Si with 0. What does it mean? It means that we have two possibilities. Zi can be plus 1 or minus 1. If Zi is from class 1, we have points. Zi is 1, we have points from class 1. When Zi is minus 1, the sample is from class 0. Then we can have greater than 0 and lower than 0 for these two. Now, for the moment, we look at asymptotically, so we assume sufficiently greater than 0, sufficiently lower, then what happens in between is, we will discuss in a moment. What that means, Si is greater than 0 and Zi is plus 1. Let's do it again on this slide because it's zi plus 1 and minus 1, si greater than 0, and si lower than 0. Again, let's draw actually, let's say these are the points from class red, blue, this W transpose X plus B equals 0. And then I have a point for which Si is greater than 0 and Zi is plus 1. Where is this point and how should I color it? If psi is greater than 0 is where? It's on this side of the separation rule. And Zi plus 1 means that it's a red point. So it's a red point that is on the correct side. So this correct side point. So this is a correctly classified point if I classify it with W. What does it mean? For my point, I have that my objective is a sum of logarithm of L of Zi Si. So if these are both positive, it means that I'm on this side of the loss, which means that my point will contribute a small amount to the loss, and the amount becomes exponentially smaller with how far I am from the separation rule. If I move farther from the separation rule, my score becomes larger and larger. Remember that here my score is 0. If this score is 1, then at twice the distance from the separation rule, my score will be 2. Then here it will be 3, 4, and so on. So the farther I am from the separation rule, the larger the absolute value of Si, and in this case, since Si and Zi have the same sign, it means that the farther I am from the separation rule, the more I am on the right on this plot. So I have that my point will contribute with a loss that decreases exponentially with how far the point is from the separation rule. A correctly classified point, a point that is correctly classified by my rule, and is far from the plane, will contribute very small, will have a very small contribution, and the contribution will decrease exponentially fast with how far I am from the point. Let's now look here. Zi minus 1 and Si lower than 0. Where is the point and how should I color it? Si is negative, so where am I? I am here, on this side. How should I color it? It's minus 1. It's blue. Again, this is a correctly classified point. Zi Si is again positive. Zi Si is greater than 0 also in this case. Si is negative, Zi is negative, the product is positive. So again, I am on this side of the loss. Again, I have a point that is correctly classified from the blue class this time, and as I increase, in this case, the absolute value of the score, so the score becomes more and more negative, my loss will decrease. So it will decrease with how far is the point from the separation rule. Let's now consider the other two cases. Si is negative and Zi is positive. It means that I have a red point, but on this side of the separation rule. This, according to my separation, would be a mistake. If I were to separate with this rule, this would be a mistake. What is the product? Plus 1 and negative. It means that I am on this side of the loss. A point on this side will have a loss that is non-negligible, and the loss, well, of course, here it's not perfectly linear, but asymptotically will grow linearly with how far I am from the separation rule. How far does it mean? the farther I am from the separation rule, the more I can imagine this point is misclassified. Why? Because this point is far in the wrong region of space. So my classifier believes that this becomes even more and more confident that this point is from class 0. So it's a mistake that becomes more and more, well, it's still a mistake, but the more I say that the point is inside class blue, the higher I will have the posterior class probability from the point being from class blue. So the more I will be wrong about the posterior probability for the class for this point. And my level of wrong, of how much I'm wrong, will increase linearly with how far I am from the separation rule. So if my point is twice as far from the separation rule as another one, asymptotically the loss it will contribute will be twice the one of the point that is closer to the separation rule. Why is this important? Well, this is important because a point like this is more misclassified. In which sense? In the sense that if I use this rule, it's true that in both cases I will make a mistake. But remember that my rule may change if I change the value of the cost of errors. So if I have a point that lies here, it will be misclassified with this rule. But if I want to reduce the number of errors from the red class, it's easy to avoid misclassifying that point. If a point lies here, before I can move to avoid making that mistake, I will probably lose all the points from the blue class. So this is a worse mistake in this sense. This is a mistake where I'm so sure that to contradict my misclassification requires that I actually make everything wrong for the other class. So the strength with which I put my class posterior probabilities influences how bad is the error, because as we have seen, the classification rule may shift when my cost of errors become different. And now, of course, the same for the other case. When the die is negative and the score is positive, I have a blue point on this side. Again, the product is negative, so again, I am in this region of the loss. So what we see is that the logistic loss will try to do what? Well, this is what happens if I have a decision rule and I measure the loss of the point. The logistic regression, when I minimize W and B, will try to move this green plane to reduce the loss. So it will try to find solutions where I have few points of this kind, maybe some misclassified points that are not much misclassified, and most of the points that are on the correct side. Imagine that I have my samples. What I'm doing is essentially I'm considering all possible rules, and among these I'm trying to find the one that is better. The one, let's say I have these three options. With the first one, what would I have? Two somehow misclassified points from the red class and one from the blue class that may have a loss, let's say, around here. If I take this second solution, I will have fewer misclassification from the red class and maybe more misclassification from the blue class, but they are closer to the separation rule. So maybe their contribution will be smaller. This last point here, what we have, everything from the red class is correct, but they have strong misclassifications from the blue class. Now, which one is best? Well, here I would have to put numbers inside to see it, but what it's trying to do is to make an average of all these costs that it will pay for the different points where it puts when I select a given separation rule, and trying to find the one that on average gives me the lowest cost for my misclassification, where the cost is measured by this logistic loss function. So we can imagine that the logistic loss function measures a cost. In this case, it's not the cost of misclassification as we introduced it in the last week. It's another way to measure how good is my classification. But in any case, we can see it as a way to measure how bad is my classifier to classify the point, Each point will have a cost because of how it is classified, and my model will try to minimize this average cost over the training set samples. So the training set samples will be used to measure the cost of my classifier and to select where a classifier is essentially a set of parameters W and B, and my goal is to find the classifier which has, on average, lowest cost, where the cost is measured, in this case, by the logistic function. Okay, let's make another 5 minutes, but just 5 break here. Just 5 minutes or 5, we resume. Okay, let's start again. Okay, so before the small break, we said that our goal is to minimize an average loss. To be more precise, we call this minimization of an empirical risk. We said we call it cost because it represents a sort of cost that we pay because of our misclassification. In the literature, you will also find it called empirical risk. So a risk is a function that measures how much I would pay for my misclassifications. It's a function that depends on the class label and the samples and measures a cost that I would pay because of how I classify the samples when the correct label is the label that I have in my training set. Now, we have used the empirical risk minimization with logistic loss function, so we're minimizing the average loss, logistical loss. However, we can imagine that we may use other loss functions that measure how good our model is at classifying the sample. So, for example, we may define, and we will see next week, another model that describes in the same way our decision rules. So it will define a separation boundary that is linear. And then whatever is on one side will be labeled as class 1, whatever is on the other side will be labeled as class 0. And the way we will find this optimal solution will not be a minimization of the logistic loss, but will be a minimization of another loss function that will measure in another way with another idea behind how good is our classification rule. So this is actually a framework that goes under the name of empirical risk minimization. As a general rule, we will estimate a classification rule by minimizing some loss function or cost function over our training set. So empirical, because it's risk minimization, because we have a risk function that we're trying to minimize. Empirical, because we're minimizing the average risk over a labeled dataset, so using an empirical dataset. Now we will see logistic loss is one example where logistic regression is one example where L is the logistic loss. We will see another example that is super vector machine where the loss will not have a probabilistic meaning. We will see it similar to the logistic loss, but we will discuss it next week, and we will give another example that, however, we will see will look very similar to this, just with a different function L. Yes? When you minimize, you can put 1 over n here, it's the same. For the moment, for whatever we said up to now, whether you put 1 over n or the sum doesn't change. So if you prefer, I didn't put it because when we introduced the maximum likelihood for the logistic regression, we didn't have the 1 over n because the likelihood is defined as the sum. Then, to keep it consistent, I didn't introduce the 1 over n, but for the cross entropy, we said I can put and then it's average cross entropy, or the risk is the same. I can put 1 over n, and it's the average risk. For the moment, it doesn't change the solution. Whether I put 1 over n or not, the minimizer is the same. We'll see when it matters, but then I will say what changes. So what we do is we minimize a risk, or if you prefer, an average risk. Actually, we see that the original SVM formulation as well doesn't have the 1 over n here, so it's not necessary that you have 1 over n also for other formulations. What matters is that you have this sum. Remember that the 1 over n can be interpreted also as part of the loss itself. So I can put the 1 over n inside L, and then it would still work. So what matters is that I have a sum of some loss over the samples. Whether the sum is an average doesn't change. An average is still a sum. Now, before we see the problems with this model, let's discuss. To now, we said that this is the function that we want to optimize, but we never gave a solution. We never said, okay, I have my training set x1 through xn and the class labels, then w is some function of x1 through xn. So how do I compute w? Now, unfortunately, we can't give an expression for w as a function of the input samples and the class labels. For the Gaussian models, we were able to give a solution for the model parameters as a function of the data, actually through the statistics of the data we have seen when we introduced the Gaussian models. For logistic regression, we can't give a closed form expression that links the optimal W to the samples and the labels. So what we will do is we will try to find numerically a solution. Using what? We'll see tomorrow in the laboratory, a numerical solver that is an algorithm that, given the function that we want to optimize, we'll call it repeatedly, and we'll call it repeatedly in a way that allows us to find the minimum. Imagine that I want to minimize this function. I can imagine that I don't know the minimum, but I have an implementation that given x gives me f of x. One way to find the solution is, okay, I will start calling this f for some point, then for some point nearby, and then I will decide whether this function is decreasing towards the left or towards the right. If I find that it's decreasing towards the left, I will try for a point that is a bit more on the left. Then if I see that it's still decreasing, I will try with a point that is farther left. Then if at some point I see that my function is increasing, I will try to reverse the way I search. So essentially, by calling repeatedly the function, I will try to figure out the position of a minimum. Now, the algorithm that we will use is a bit more refined than what I just said here for a one-dimensional function. It works with multi-dimensional, and it's actually quite efficient in the way, in the number of calls it does to find the solution. Maybe I will say a couple of words tomorrow, but we will not see how the algorithm works in detail. The algorithm requires that we are able to compute the loss and the gradient, that is the vector of derivatives of the loss with respect to the parameters. We'll see tomorrow how to do it. So essentially, we need to be able to compute this sum over I of the loss. And actually here, if you want, you have to put B as well, because we have the bias in the logistic regression. Then we need to be able to compute the vector derivatives of the loss with respect to the different components of the vector W. And then the derivative of the loss with respect to the bias. We'll see how to do it implicitly tomorrow and how to do it explicitly if you want a more efficient solution. So tomorrow we will discuss, or it's not tomorrow, yes, it's, no, the laboratory for this is next week. So next week, when we see the laboratory for this, not tomorrow, I think we finish this lecture for the part that remains. But next week, when we have the laboratory on this, we will see how to make this work in practice. Now, what remains to discuss about this binary model are extensions of the model that deal with some issues that are intrinsic to the model. The first of which is that the model is prone to overfitting. How can we show it? Well, remember that overfitting means that the model is not able to generalize well to unseen data. One easy way to make the model overfit, where it may not be evident in an intuitive way that it's actually the same effect of overfitting, but where we can at least see why the model is failing badly, is the case that is easiest to solve at all. The model we have performed will not actually find a solution and is not well defined. Essentially, it will obtain an infinite overfit for a task where my training samples are perfectly separable. So if I have a data set like this, which may look like the easiest thing to do, then whatever we discussed up to now will not work anymore. Why will not work anymore? The problem is that I have infinite number of planes that separate the classes. Not only that, let's take one of these planes and let's represent it with some W1 and bias B1. Then if I have a plane that perfectly separates the classes, what does it mean? Remember the logistic laws? Here it decreases as exponentially of minus ZI. For all planes that perfectly separate the classes, all my samples will have ZI greater than 0. If the plane separates perfectly my training set, all training samples will be on the correct side of the plane. So for all the points, this holds, okay? Which means that now, if I have, for example, a set of W and B, this corresponds to S1, S2, S3, S4, etc. Sn. Each of these corresponds to log of 1 plus exponential of minus Zi. Sorry, let's multiply it by Zi, otherwise it will not work. Zi Si, which we said decreases exponentially as Si increases. Now imagine that I tell you this is a solution that perfectly separates the plane, the classes. Now, and then I can compute its loss. If I take the solution 2W and 2B, does it change the separation surface? Well, the separation rule is W transpose X plus B equals 0. So let's now call this W1 and B1. For the new point, it's for the new plane, this is the separation rule. But this is 2W transpose X plus 2B equal 0, which is the same separation rule as before. The solution for the first equation is the solution of the second. So the plane is the same. I just doubled the norm of W. What happens to my loss? Zi and Si all remain with the same sign, because if I double W and B, if Si was W transpose X plus B, Si1, the one computed with the new values, will be what? Will be twice Si. So the sign will be the same. So the new loss will be what? For each point, I will have now the score, the new Si. So I will have Z1, S1, 1, Z1, S1, 2, so the one, S2, 1, the one computed with the new W, and each of these will be twice the original one. But if I double my Si Zi for all the points, and for all the points I'm on this side of the plane, what happens to my loss? For all the points, my loss will decrease. So the sum of the losses will also decrease. That means that this W cannot be optimal. Now I have a new W that is better. Now I repeat the process. I take 2 W1 and 2 B1, and they call this W2 and B2. What is the loss of the new W2 and B2 with respect to the W1 and B1 solution? The separation rule is the same. And again, I have doubled my scores, which means all my ZI is doubled. So my loss has decreased for all the points again. So every time, if I take one solution that correctly separates the plane and I compute some alpha that is greater than 1, that solution, I get a new solution where I'm increasing the norm of W, the separation surface remains the same, the loss becomes smaller and smaller. When this will stop, it will never stop, because the loss will asymptotically go to 0, but I will achieve 0 only when S is infinite. So I will never achieve 0, but every time I increase S, I will decrease my loss. So numerically, the solution does not have a minimum anymore, and it just has an infimum obtained for norm of W that goes to infinite. Norm of W goes to infinite. What does it mean? It means that if I'm not on the separation rule, as soon as I move inside one of the region, my class posterior probability will become 1. Because I have, for a point that lies here, I have sigmoid of SI, but SI is a very large number, because if W, the norm of W goes to infinite, then as soon as I'm an epsilon inside here, SI becomes a huge number. So as soon as I'm a small step inside one of the region, my class posterior probability becomes 1. The model is sure that whatever is on the right of this plane must be from class 1, and there is no exception to that. And whatever is from the other class must surely be from class 0. Now, this is an example of overfitting. Why? Because if I had few samples, then probably I would have seen that there may be few samples from each class on the other side of the boundary. I just didn't see them because probably I didn't have enough samples. So this is an example of extreme overfitting. The model becomes overconfident on the training set. Since for the training set, it says that the probability of all the for all the red points, it can say that this is 1, and for all the blue points, it can say that this is 0. It will do that. We are minimizing cross entropy. It can match the empirical data distribution by taking a W which has a norm that goes to infinite. The larger the norm, better the match with the empirical prior distribution, with the empirical class posterior distribution. Which means that this is an example of overfitting when I'm overconfident for the training data. All the training data are perfectly classified because I matched the empirical distribution of the training data, but that does not necessarily reflect the fact that it does not reflect the fact that probably I can have points of the two classes in the other region. I just had a few samples maybe, and then that means that I didn't see any of these points just because my empirical set is finite. So this is an example of extreme overfitting that actually makes our solution, well, numerically we are not able to compute it because we will get at some point some inf in our computations. From the theoretical point of view, it's an extremely overfitted solution that we can't compute, but we can see what's the trend. The trend is trying to say that whatever is on one side of the hyperplane is surely from class 1, and whatever is on the other side is surely from class 0. Now, how do we avoid this problem? Well, one possible solution is, okay, what was happening? We had separable classes, then the model was able to minimize the loss by making our norm of W grow in an unbounded way. So unbounded growth of the norm of W allowed the model to perfectly predict the class labels for the training set. We can then say, okay, let's try to avoid that the model goes to sorry, here I didn't explain it why. Let's try to avoid having large norm of W's. Large norm of W's corresponds to models that may be overconfident, especially if I have few samples. That means that I'm more keen to overfit. How can I do that? Well, I can add a term that penalizes solutions that have large norm of W. Now we can give other reasons why these terms of this kind are effective, and when we discuss super vector machine next week, we'll give another interpretation of what this term is actually doing in a different context. For the logistic regression, we can imagine that we have seen in the case of linearly separable classes, but we can imagine that if there are few errors in my data set, then something similar is happening, not that to that extent, but in any case, if I have few errors, I will get to overfitting, and overfitting will typically correspond to solutions that have a large norm of W. I can try to reduce the impact of overfitting by asking for solutions that have lower norm of W's. These solutions will have, in general, a larger loss, because requesting low norm of W means that even if I'm able to find solution where most points have a very small loss and few points have a significant loss, having large norm of W means that I'm actually taking a large amount of points and increasing by a small amount their loss, but overall the global loss will increase, because remember that this decreases exponentially. So if I move these points back, I'm increasing their contribution exponentially. So I will have a worse loss, but the model will have a low norm, so it will probably overfit less. And how do I balance these two terms? Well, for what we see, we can do it by having a loss function that tries to balance these two terms by adding them together with a weight that controls how much I want to limit the influence of the norm of W, and we use the square norm. Well, because it's, well, for practical reason, well, first of all, square norm is differentiable. The norm of W is not differentiable everywhere, because it has a spike. It's like taking absolute value. So V squared, the derivative is 2V. The derivative of absolute value of V is a function that does like this, so it's not differentiable everywhere. So even just for practical reasons, we take the square of W. That's not the only, but we can give other interpretations where it makes sense that this is squared, but we don't have time to see them. And we have a coefficient lambda that is a hyperparameter that will control how much we regularize, this is called regularizer, how much we regularize our objective function. How we estimate lambda? Well, it's a hyperparameter, so we will typically use cross-validation. Large value of lambda means we want low norm, so we allow ourselves to do a worse work on the training set, but we try to reduce the risk of overfitting. Low value of lambda means that we don't care about overfitting, we want to have the best we can on the training set. Typically, if we have loss of data, then we can ignore the regularizer, because if we have loss of data, then our solution will typically generalize well, even if we optimize the training set, because if we have loss of data, we will also have loss of errors. So we will not have the case where the model can be overconfident on the training data, because there are too many training data to be confident about. While if I have few data, typically I will want to regularize to avoid the risk of overfitting. And of course, the larger the space, the more the number of parameters, so the more freedom the model has to find an overfitting solution. So the larger the input space, the more relevant will typically be that I add regularization. If my input space is small, I will probably not need to regularize much or even at all. If my input space is large compared to the samples, again, I will probably need to regularize to avoid the risk of overfitting. How much? It depends on the data. So I will typically try different values of lambda using a model training in the validation dataset. On the model training, I will fix one lambda. I will optimize my objective, and then I will measure how good is the model for the validation data, as we did up to now with all the hyperparameters. And then I will select the hyperparameter lambda that gives me the best results on the validation data. Now, in this case, typically you will find this is called a regularized risk minimization, and in this case, typically you will find the 1 over n expression here, so the average loss. Notice that the two losses are related, but now if I move from one to the other, I need to scale also the value of lambda. Since I'm optimizing with, I'm looking for a best value of lambda through cross-validation. In any case, it doesn't really matter, but mathematically now minimizing the two functions will be equivalent if I also use the equivalent value of lambda. Now the lambda is not the same anymore, but in any case, this is how you will typically find a regularized risk minimization function written, and this lambda is a hyperparameter that we will estimate by cross-validation, and the rest of the parameters are optimized as we have seen. Notice that we can't optimize R with respect to lambda, because if we try to optimize R with respect to lambda directly together with W and B, then the minimum, if I put lambda here and then I look for the minimizer of this function, I will trivially find lambda equals 0 as the minimum. So lambda is exactly what we said the hyperparameter is. A parameter that I cannot optimize directly using the same objective function that I use to estimate the other parameters. W and B are obtained by minimizing R, but lambda cannot be obtained by minimizing R with respect to lambda, because then I would trivially find the solution lambda equal to 0. So for lambda, we use cross-validation. Now, of course, this is part of a bigger framework which is called regularized risk minimization, where I have an empirical loss, as we have before, plus a regularization terms that penalizes solutions that should be penalized because they typically tend to represent bad solutions, for example, because they represent overfitting. In our case, we can interpret this as being a solution that represents simpler separation rules, where simpler means the model is less confident, so lower norm means the model is less confident. Then for the SVM, we'll see why it's a better solution to have low norm of W in that context. And in any case, the two terms play the same game as we have said with when we talk about overfitting. One tries to, the first term, the norm of W, tries to reduce the amount of overfitting. The other tries to make the model work well on the training set. So that means that if I have low, I want both to be low. Why? Because having a good classification of the training set is necessary to have good generalization. On the other hand, this is not sufficient. So having a low norm of W improves the generalization of the model. Both on their own are not sufficient, because if I have good generalization, but I make bad classification on the training, I may be able to generalize a bad solution, which gives a bad result. If I have a very good solution on the train that does not generalize, then I'm not able to generalize a good solution, so I will have bad solution as well. What I want is a solution that does possibly well on the training set and possibly generalize well. So I want both to be small. Of course, this is not possible. I need some trade-off. I need to find the trade-off that allows me to do well on the training set, but still generalize to new data. And this is controlled by these two terms. And then here we have, let's see how much time we have. Okay. Let's just see this plot. We have examples with regularized and non-regularized models. Non-regularized is on the left, regularized is on the right. You can see that the non-regularized model tends to give predictions that are much more confident. This is the separation rule, W transpose X plus B equal 0. Points on this red line will have W transpose X plus B equal to 5. So according to this model, here the probability of class 1, given the samples on this line, is sigmoid of 5. While for this model, the probability of samples on this line, well, notice that the orientation is also different, but let's take this line, points that are at this distance from the separation rule will have a probability of being from class 1 that is sigmoid of 1. So here the model is less confident. When I'm in this region, I still have a large probability, a non-negligible probability that the sample is from the blue class. While this model is more confident. As soon as I move a bit from the separation rule, I become quickly more confident that the probability for the red class is large. Now, if I have enough data to actually avoid overfitting, the solution with lambda equal to 0 is best because it gives us a better model of the class posterior probability. But if I don't have enough samples, then if I don't regularize, I risk overfitting, and then my posterior probabilities will be overconfident with respect to what they should. And what does it entail, we will see next time. Okay, so let's stop here. Tomorrow we will finish with this part.